That's weird counting, Pamela.
Yeah.
It's like an extra That was an extra 2. Are you on daylight saving seconds? Oh,
They should launch rockets that way.
Yeah. I think Nancy should stick around for the pre-show too.
I think so as well.
Yeah, I think that'd be cool.
She's
And that
fun to
way
chat
people
with.
can just see and hang out with Nancy just like we do now every week, which is awesome.
Yeah. Nancy knows everything.
Pretty much.
Yep.
Yeah. Yeah.
I'm
I know she likes to be the wizard behind the curtain, but
Yeah.
When you're the wizard behind the curtain, that means you know everything.
clearly.
It's kind of amazing.
Yeah, exactly. Yeah, so how are you all doing?
Recovering from daylight savings time.
I know. You've heard they
Yeah.
want to go to permanent daylight saving time now next year.
Yeah.
All the sleep experts are really mad.
Yeah, I can go on record. I think we should go to permanent standard time.
I agree.
I'm with you.
Yeah,
I don't care.
Arizona already does it. Does
Yeah.
does British Columbia, somewhere in Canada? I know they don't do it.
Saskatchewan.
Okay.
Yeah. Yeah, Carla's going to kill me for this, but I would rather have it get darker earlier so we can have more nighttime for astronomy.
Viewing, yeah, that's the thing. Now I already have to wait till 8:00, and by summer it's like
That's
10.
an excellent reason.
Yeah, summer it's
The
like,
physical and
for us
mental
it's
health benefit.
10:30 where I live for it to get dark. And I have normally have been in bed for an hour. So if we can push it an hour earlier, I think that would be better. And I like
There's
to get up
pretty
in the
good-
morning and have some nice sunshine on my face. So I'm with the sleep experts. Let's go to daylight. Let's go to standard time. Not there. You go. Serious Keely is saying UTC. So yeah, let's just go to Universal time. So it's
I've thought of that too. Yeah,
3 in the morning right now. What time is it? No, it's midnight.
and
1
all
in the
call
morning?
it the same thing because the military calls it Zulu, and you also hear it called GMT. I think it should just be called UT, Universal Time. It's all
I
the
can
same
go
thing.
with Zulu just because I'm a controller.
Zulu sounds cool,
Yeah,
but
Zulu sounds pretty good.
Doesn't it
Yeah.
though?
And GMT does sound a little Greenwich centric.
yeah,
Yeah.
Greenwich centric.
Touch Greenwich centric.
It is pretty cool though. Have you been to Greenwich? Have you actually?
Yes, I stood on the Prime Meridian.
So have I. Yeah,
Yeah.
There's not a lot of places you can sort of be, and that's one of those places that just you're like, okay, like history unfolded and was incorporated from this very place, which is pretty cool.
The 90th meridian.
Oh, cool.
I am a
Is there a marker?
quarter turn off of Greenwich.
Is there a marker there? Or
Yes, yes.
oh, cool. I haven't seen that.
Really?
We have the. I'm in between the 58th and the 59th parallel.
Do
So
people just know this?
Isn't that the border of
I
Canada? Isn't the U.S. border the 58th? Or it's I think it is.
yeah. The border is the 58th, and then the 59th is partway up Vancouver Island, and so we drive past it.
Feeling like I should know where I am in the coordinates.
There are a few people that know this stuff really well. In Canada, it's popular to talk about what latitude you live at. Like Edmonton enjoyed making fun of most of the people in BC because we were north of them. And then Fort Mac made fun of us for the same reason. But they're Fort Mac, so, you know.
It's kind of like a hardiness thing. Like
it is
like
exactly that.
Yeah, so the more north you are, by default, the harder your life is. And that you then, by doing the same things as the southern folk, you're just guaranteed to be better and tougher. That's the way it works.
I've been to the equator in Ecuador too, but there's a lot of not the equator. Like there's a lot of claims to it because it moves around a little bit, by about half a mile or so. So the equator's not a perfectly stable place.
There you go. People are saying it's the 49th, right? Okay, so I'm between the 49th and the 50th. Yeah.
Yes, I was pretty sure Edmonton was 54th, and that would have made it in your metric about 4 degrees into the U.S., which is slightly awkward. Sorry, there's a fly buzzing around my head.
This is going to be fun. All right, I think we've reached the beginning time. So just everybody, actually, you know what? I'll explain it in the show. So we'll just get on with the show.
Can you check your mic first? I'm not sure you're on the right mic.
Me?
Yeah.
I am on the right mic. This mic. This mic.
You're just not sounding as good.
It's one of those times when I regret the decision to wear earbuds.
I'm going to have to switch it. My headbud's chirping at me, so I'm going to have to switch over.
Okay, let's go for it.
Okay. All right. Hello and welcome to the Weekly Space Hangout for Wednesday, March 16th, 2022. I'm Fraser Kane, publisher of Universe Today. With me, we've got... Actually, you know what? That's me going into the Astronomy Cast intro. So this week, we're going to be talking about Apollo 17, Artemis, Space Launch System. Finally, James Webb is focused. Hot stars on I can't even think about anything. I give up. Hot spots on magnetars, Ingenuity extended, and how would a Mars sample return mission work? Joining me this week, we've got Dave Davidson. Hey, Dave.
Hey, still here in Norfolk with a dead headset, so I just switched over.
Okay.
I thought, hey, I'm going to try my wireless headset, and then it started telling me battery low, so I guess I'm not going to be trying it.
Yes, yeah. We've got Dr. Kimberly Cartier. Hello, Kim.
Hello, Fraser. Happy podcast day. It's been a while.
Mm-hmm. And we got Dr. Nick Castle. Hey, Nick.
Hello.
And a fly.
And a fly.
Yeah.
Because why not? I think they just come to me because I turned really old this past week.
All right. So I don't even make a joke about it. All right. So before we get into the rest of the show, I want to give a big shout out to our good friends, fans at the Weekly Space Hangout crew. They are executive producers. They call the shots. We do what they say. They organize our every waking moment, and we couldn't do it without them. So if you want that kind of executive cosmic power, go to the weekly wshcrew.space, and they will give you all the information that you need. Now, we have a special guest interview with Nashanty Brunken and Dr. Alice Booth about the largest molecule detected in space in a planetary disk. It's pretty great, but it's pre-recorded. So it's going to come at the end of the show, as all pre-recorded interviews do. It's about 11 minutes. So we will go to about the 48-minute mark, and then we will switch over and play out the interview for the rest of the episode. So stick around. It's a great interview, but it's not live. So, all right, let's get on with the news. Dave.
Yes.
SLS, Artemis, Apollo 17. How's it all play together?
This is an interesting article that just caught my eye on Apollo 17, which was the last mission to the moon in 1972, that they are actually opening just now some of the samples and doing science on them, actually, to kind of as a preface or prelude to Artemis going to the moon in a couple of years and bringing back samples. This gives them a chance not only to actually use some of the newer instruments we have on the samples, but give them look at the techniques. This is at the Johnson Space Flight Center. This is the Next Generation Sample Analysis Team. It's a joint NASA European Space Agency team that started doing this in 2019. And they're actually using some of the newer X-ray techniques they have in order to open these samples and take a look at them.
It's quite the foresight to know that better technology was coming, and so they left a bunch of the samples completely sealed up.
Yeah, these are legacy samples. And they're going to be doing the same with OSIRIS-REx, which comes back at the end of next year, too. I remember reading that there will be legacy samples put ahead, assuming that generations from now, there's going to be better techniques that we can use to look at these things. You can even tell from that one slide that's up there, the bottom is an X-ray of the same tube that was sealed in 1974, 2 years after Apollo 17 brought this back. The top is the X-ray of the tube with modern techniques looking at it. So you can actually see a lot of the resolution and difference just looking at it. And, they're finding things like that the weathering is different down through the core on the sample, and they're seeing like evidence, because there's space, solar wind and things like that are interacting. There's ejecta from other asteroid and meteor impacts on the moon. So there is some action going on looking at the core. And Artemis 1's rolling. Oh, go ahead.
Oh, how does this tie in then to the Artemis missions?
Well, this is a new generation. They've never really looked and done these kind of sample returns. It's been a while since we brought anything back from anywhere, really, since the Apollo missions were 50 years ago to this year, practically. So it just gives them a chance to break down. And Artemis should be, I believe it's Artemis 4 in 2025 is going to be the first crewed landing down on the poles. Now we're going to land somewhere. The Apollo missions never landed anywhere beyond the near side equatorial regions of the moon. So they're actually going down to, they haven't announced an exact landing site, but they know they want to land somewhere down toward the lunar poles eventually with the Artemis 4. First crewed one should go out 2022, 2023. For the one going out this year in May is actually rolling out tomorrow, Artemis 1. And that's finally the first SLS launch of the Space Launch System, which has been, I think James Webb is the only thing that's been delayed longer than the SLS, and now it's finally going in May. So tomorrow, that's going to be a big deal to see the whole rocket stacked together with everything. Again, this one, Artemis 1 uncrewed, a lunar free return kind of Apollo 8 style mission out around, it's going to be a shakedown for first launch of SLS. They launched the Orion capsule a few years ago, but it was on an Atlas 5, I believe it was. It wasn't on an SLS rocket.
Delta?
So
it was on an Atlas.
So Orion has been to space. The capsule's been to space, again, uncrewed. So this will be the first flight of the full up, minus the crew, of course. So it's a little depressing when you see the cadence, the launch cadence for SLS and Artemis. We might see a launch a year, maybe,
and
which
the
is
price.
This is one of those ones we've been chasing, like space missions to watch next year, and it's been bumped year after year after, along with James Webb. It's like maybe it will launch in 2020 or 2021 or looks like 2022 is the year. So
an auditor put it at $4.1 billion per launch.
There is a lot of controversy around this too, just for the price tag. And the idea is like, well, SpaceX kind of has a Falcon Heavy now. Do we both need both? That could potentially hoist crewed capsules to the moon as well. So there is some controversy out there.
Crew Dragon is bigger than the Apollo capsule, like twice the size. It's twice the internal volume of the Apollo capsule. The Orion is bigger too. So in theory, you could do these missions with Crew Dragon and Falcon Heavies. But anyway, this is a
and remember back about, was it 2009, 2010 with Ares 1, and we were all like, oh, we're going to the moon again finally. And then they did the first suborbital launch for, was it Constellation, I believe was the program, and then they canceled it. So it's
well, I mean, it's SLS. I mean, did they really cancel it? It's SLS. Awesome. That's really cool. I think we've got a photographer from Universe today who's going to be out at the rollout tour. And it's not the actual launch. This is just everyone take a look at our really big rocket.
I checked right before showtime. They're saying not earlier than May right now they're not pinning a date. Capstone, which is part of the whole program that's going to be going and testing the Pathfinder for Lunar Gateway, which is part of Artemis. That launches May 3rd. So that's going on a Rocket Lab Electron rocket from New Zealand.
Yeah.
So that's going to be an interesting mission.
Kim, James Webb is in focus.
It's in focus. It works. It works.
Are we safe now?
According to the panel of JWST scientists this afternoon, we are safe. We are past all of those points where if we didn't make it past that point, there wasn't much point in continuing.
Right.
because it would just not work. So what you're looking at here is the first perfectly in focus image from James Webb Space Telescope, which is just, oh my God.
Yeah.
So amazing. A couple weeks ago, we saw an out of focus image from the telescope from one of the early alignment phases, where we saw, one of the hexagonal mirrors all lit up, and we saw 18 different reflections of the same star, and we were all like, oh, this is amazing. We're getting light. This is great. Now we have all 18 mirror segments in alignment, like perfect alignment. Better than 100 nanometers alignment between 18 giant mirror segments, which is way better than specification. They're all pointed at one star right in the middle. It's a random star. There's nothing special about it on purpose because, you just
apparently it's 11th magnitude.
Yeah, it's it's a V 10.9 or something.
Yeah.
Super faint. Can't see it with your eyes.
Yeah, you would need a backyard telescope to be able to even see this star.
Yes. So this is not a naked eye star at all. It's super boring. It doesn't even have a name or a fancy name. It has I don't know, 18
it's an HD
long
designation. Yeah.
Yeah, telephone number. But what is really excellent is the fact that all of the segments of the mirror are perfectly focused. They're perfectly aligned. They're sending all of the light together, focused into the near infrared camera. And it produced this image, which is essentially the first deep field image that we're getting from the telescope, because not only do we see the central star in focus, we also see all those background points, and all of those background points are galaxies.
Yeah.
There's a couple of background stars, but most of them are galaxies. And we're just seeing, literally, I took that one image and I just zoomed in as far as I could. And you can see just the amazing resolution of just, this isn't even a science image. This is a technical alignment image. They're not even trying to make it look really fancy. And this is the kind of resolution that we're getting. You can see spiral arms. You can see multiple galactic nuclei amidst a giant fuzzy cloud. Maybe that's a merger of some kind. You can see clusters of things together. In one of them, you can actually see among the spiral arms, brighter hot spots where maybe there's a lot of star formation going on. And this is a deep field we have never seen before.
Yeah,
this is not anything that Hubble looked at. This is just a random spot in the sky.
So I think the thing that's really important to know about this is that the star is only mildly overexposed. And so, Dave, when you think about your astrophotography work and you look at that at the star that's in the image, that feels like it's a 30-second exposure, maybe a minute-long exposure, right? With a telescope. I suspect it's nothing longer than that. It's getting oversaturated. It's starting to blow out all the pixels around it. So
it wouldn't be a astrophotography picture of the day.
No. And yet it is deep fielding.
It is
all this
random part.
All these galaxies around the back of it, galaxies that have never been seen before.
Yeah, and cool. I think there's only one of the galaxies in the image that that someone was able to match to, I think, a Pan-STARRS image to sort of try and get the redshift, and it's still 5 billion light years away.
How deep magnitude-wise are these galaxies it's looking at? I haven't caught that.
I don't know that I caught that number either.
Yeah.
I think
there are a couple new matches appearing on Twitter, so people are analyzing this in real time.
The closest one was 1 billion light years. The Pan-STARRS one was 1 billion.
Yeah.
And then they're farther than that.
I remember writing about James Webb. We were trying to quantify. You saw the number 1,000 times more powerful than Hubble, and then somebody did pose a question. It's well, how do you quantify that? And I'm well, maybe if they're talking in terms of how much deeper magnitude-wise at that infrared wavelength, you could say 1,000 times, which is, 5 magnitudes difference is 100. Oh. Or is that just a number that people are just throwing around that has no basis behind it?
And so, like, just imagine when they point this telescope at a spot in the sky that doesn't seem to have anything in it, and they
take a deep field with the intent of taking a deep field, which is
taking a
what
proper deep field.
a proper deep field image, which they do plan on doing at some point. They have not yet told us when, because all of their super secret first light targets are super secret.
Yeah, no one will tell us.
But yeah, we got focused light from the giant mirror into one of the instruments, which is just phenomenal. It's an amazing milestone to reach. And we, at the literally at the very least, we will have this one instrument. But at this point, they are incredibly optimistic that everything will go very smoothly in aligning the mirror with the other instruments on the telescope. That's, the near-infrared spectrograph. There's a mid-infrared imager, and there's the near-infrared imager and spectrograph. I know all the acronyms they stand for. Is sometimes escapes me. NearSpec, MIRI, and NEAREST. 3 more instruments to go that they have to align. Those are going to come up in the next month and a half or so, 2 months to 2 months. And then once all of that is done, there's going to be 2 months of science, alignment and getting all of that ready. And then and that should be done by the end of May. And they're predicting maybe some first light images by the end of June. But they've not told us what that will be.
I'm really glad they're sharing the bits and pieces and the improvements and the changes in that. This feels different than any other telescope, and maybe because everyone's so excited, we all want every little bit of information. But even just show us like blurry bad pictures and go, don't worry, it's getting better. That's a brave move, because people would take it the wrong way.
There has been so much riding on this telescope for so long, and they've gotten so much bad press with all of the delays and how much more it has cost than expected, and the screws that got dropped in places where they shouldn't have gotten dropped inside the remember that part where there was just screws that were dropped inside the telescope? There's been so much flack, and there's been so much talk about, it's going to be out at L2. You can't go out and fix it. What if it goes wrong? If it goes wrong, you've wasted all this time and money. And I think a lot of the sort of the press that they're doing and all of the commissioning stages and just showing all of the progress that it's going through as it's getting ready for first light is in part to address all of those questions and problems that they've had in the past, and also to reassure people that you're gonna have to wait a couple months longer, but it's definitely going to be worth it.
But like just this picture, there is science in this picture right now.
There are people all over the interwebs right now, like analyzing this in detail, comparing it to other surveys, from other telescopes, and pulling out some amazing science already. I think one of the scientists said this came in, I think, Saturday evening, and she spent all of Sunday morning in her pajamas, holding a coffee, staring at this, and just basically geeking out over how amazing this is and how much science we're going to get even from this one image. And there's going to be more of these types of images to come even before we get to first light.
Yeah, absolutely phenomenal.
The first thing that went through my head seeing this picture was, that's a lot of PhD theses right there.
Yeah.
Oh, yeah.
Yeah, this is going to be a PhD machine.
I'm excited for the exoplanet science they're going to be doing with it, too. It's kind of interesting.
Oh, yeah.
Me too.
Very much so.
Everything. The studying stuff here in the solar system, the exoplanets, planetary disks, peering through the dust, looking at the core of the Milky Way, looking at galaxies on the other side of the Milky Way, and looking at stuff at the beginning of the universe. This is a Swiss Army knife of goodness, and it's going to change our understanding of the universe. It was, it's just amazing of just what. I can't believe we're here. I just can't believe.
I know.
Literally, I've been reporting on this story for my entire career,
I've been reporting
Here
on
we
this story
are.
since I've been on Weekly Space Hangout.
Yeah.
And everyone who has watched knows how skeptical I have been that this would actually work.
Exactly.
And now you can see how giddy I am that it actually is working.
I can show you the end of the year articles for the last 5 or 6 years that said coming next year, SLS James Webb, maybe.
Yeah.
Like, you know,
Yeah. Well, congratulations to everybody involved in this. It's a phenomenal first step. We appreciate you putting it live to us so we can see it, and we cannot wait to see what happens next. Awesome. All right, Nick, Ingenuity got an extension.
Yep. So this is one of those wonderful examples of NASA engineered something, and specifically the engineers at JPL engineered it so that it worked way better than expected. So this was intended as a technology demonstration. We didn't know a year ago if we could fly a helicopter on Mars, if we could fly anything on Mars. The other picture is actually the right one, Pamela. This is so the engineers were quoted as saying, we'd be impressed if this thing worked out for 3 flights. We'd be floored if it made it to 5. We finished 21. And the 22nd is scheduled, actually for March 19th or a little bit thereafter. It's one of those no earlier than deadlines. This, by the way, is from some of the first commissioning of it, where they're demonstrating that the rotors would spin properly before they did the first flight, which was all of, I think it was 39.5 seconds or so. It's now traveled multiple kilometers. I always forget the numbers. I can look them up just as well as our viewers can. They're now looking at doing much longer flights and really starting to implement this as not just a proof of concept, but a demonstrating the use of it concept. So this is where they're really demonstrating the technology. And one of the things that's really interesting about this is it covers ground a lot faster than the rovers can. Even Perseverance, where they've tried to engineer it for moving as quickly as it can on this platform, if you're going 100 meters in a day, you did a lot of driving in that day. Ingenuity leaves that in the dust. The next flight is scheduled to be something like 350 meters in one hop. And what's cool about that is it's giving higher resolution images of all of that ground ahead of it, much, much better than what we have to navigate off of in the absence of something like this, which is usually a combination of orbital data and what we can actively see from the rover at the time, which means if there's a little bump in the road, we have no idea what's on the other side until we actually get up on that bump. And then you have to either rely on software to figure its way through or stop, wait for the pictures to come down, and design a whole new drive just to get past that bump. Because the last thing you want is to drive over some nice pointy sharp rocks and destroy your wheels, because then you've got a wonderful stationary platform for science instead of a rover.
Are we going to get to this point where Ingenuity and Perseverance are working as a team in a more comprehensive fashion? Like right now, it's really Ingenuity's been off on its own, proving that yes, indeed, it can fly, it can take pictures, it can land, it can move sideways, it can raise altitude, like it can fly. We get it, Ingenuity. You proved that. Now, do some work. Is it ready?
Well, it is doing some work. Where it's looking at places the rover isn't likely to get to, or that they've already assessed that it just won't be able to get to. And so it's taking pictures of areas that we're not in. There's actually been a lot of development work, actually in anticipation of Perseverance. There's a funded project called Sandy that's looking at specifically from an operational standpoint, how do we couple using a helicopter, a little gyrocopter like this, along with a larger rover package to optimize how quickly we can drive and do that assessment and make it so we can get from interesting science spot to interesting science spot faster without missing anything. Because you both don't want to endanger the rover and you don't want to miss the science that you could have gone by. So I hope that they're working in that direction. It seems like they are. We'll see more as it goes.
Yeah. I can't imagine
the extension,
any
by the way,
mission...
is through September.
I can't imagine any future mission not being equipped with a helicopter from this point on.
Funny the Mars
astronauts are just going to be hurling these things around. They're going to have drones for days.
That would be pretty cool. I actually love the way they visualize that in the National Geographic TV show Mars, where they're looking at using these little drones to fly around. That's absolutely based on Ingenuity and the concept of where might this technology lead us. If you can do the quick and dirty assessment from flying by to highlight what targets you want to do the more detailed stuff with, you are rapidly increasing the cadence of what science we can do.
Yeah. And so again, you can imagine these like automated algorithms where the helicopter flies out, scouts out a pre-programmed chunk of the terrain in front of the rover, delivers all that material back. The rover then makes decisions about how it wants to actually navigate. It's identified all of the interesting targets. Again, like Perseverance wouldn't necessarily even notice a really interesting rock that's just 10 meters to its right side over a little bit of a ridge. And so in this case, you're going to get the everything. Definitely stop and look at that fish fossil.
Well, here's hoping on that one. I'd love to see a fish fossil on Mars. That would just
did you
imagine how many fish fossils Curiosity has just gone right by and it didn't even know they were there.
Did you see the flower that Curiosity saw? Well, flower in air quotes.
Yeah.
The flower-shaped dendritic mineral growth?
Yes.
I saw that one.
Yeah, we talked about that a couple of weeks ago.
Yep.
Yeah, that's awesome. All right, very cool. Again, congratulations to Ingenuity. What a good time for space. Space is the best. Dave, a hotspot on a magnetar.
Yeah, this came out of a mission you don't hear a lot about, but I think is kind of cool. It's called NISR, the Neutron Star Interior Composition Explorer. This is an X-ray detector that's placed on the outside of the International Space Station, one of the astrophysics missions. And I think that ISS doesn't get enough credit for some of the astrophysics laboratory things that it actually does, like with the AMS-2, the Alpha Magnetic Spectrometer, NISR, Sextant. There's a fair amount of astrophysics going on, missions that take advantage of having the platform of the ISS with its solar panels, and it needs a massive amount of power, that you might not have in a free-flying satellite. So this magnetar was sighted first by SWIFT, which actually is looking at gamma ray bursts, but it has a battery of instruments, UV, X-ray, visible light, and it actually picked this magnetar up that is named, it's got a phone number name as well, SGR, as in, it's not actually in Sagittarius as I looked it up, but I think initially there was some confusion. So it's actually in Scutum, which is a constellation very nearby. SGR 1830-0645, which is the ascension declination coordinates. That's where I started sleuthing it out to see actually where it was. But Swift saw this initially, and Swift is in orbit as well, not on the ISS. And they aimed NISR at it, which looks at in the soft X-ray regime. It looks like a big box type thing. There's some very interesting GIFs of it rotating, actually. It has 56 X-ray detectors that look in the soft X-ray regime. Again, something you couldn't do from Earth. That's why they do it up in low Earth orbit. And they noticed this magnetar is spinning a little faster than once every 10 seconds. Magnetars are about neutron stars 10 to 20 kilometers across, very small, very dense, spinning very fast. And they noticed that the timing on it, that there were some secondary bursts. This simulation that you see up there just kind of show the idea of it spinning and flashing.
Yeah, this isn't a real picture. This is a artist illustration.
There is actually on the NASA site there for the article, there was a animation of the X-ray merger, kind of where you saw the signal merging. But they noticed these timings were quickening in these little secondary flashes, and they realized that this surface event that's going on there, that you see the big X-ray flash, is actually condensing. It's the first time they've seen one condense. And I think it's just cool that 16,000 light years away, we're seeing some kind of surface detail on something. We're seeing activity per se, not like that's actually, that's an artist's conception right there. But you're seeing evidence of something going on the surface of something 16,000 light years away, I think is kind of interesting.
So do we know what caused this hotspot?
This is what I saw in the article, that this is just magnetars. This is an eruption in X-rays. You can only imagine what's cracking the actual crust of something. A magnetar crust must be very dense. So there is a lot of models out there that are trying to look at exactly what's causing that kind of X-ray burst. But it's, as far as they know, it's just merging into a more powerful burst right now. It's obviously something Swift hadn't seen before 2020. So it's a transient kind of activity.
I'd heard that it's like, as you said, like shifting, almost like tectonic plates on. Like you get little mini earthquakes, little crust deformations.
But I can only imagine, again,
quakes. Yeah.
To think of a magnetar crust must be like extremely dense. For anything to actually like disturb that must be incredibly powerful.
Well, I mean, neutron stars aren't just like a ball of spinning neutrons. They actually have layers. So they have, like, the top layer is mostly like protons and electrons mixed up, and then as you get closer and closer to the core, it turns into more and more just neutrons. And so you can imagine even those, bits of it shifting, pockets turning into more neutrons, and you getting these shifts. I mean, the other big mystery with magnetars is just like, why do they magnetar?
No, I think I learned this from Astronomy Cast. Not all pulsars are neutron stars, and not all magnetars are pulsars. Or do I get that?
Wait, hold on. All magnetars and all pulsars are neutron stars.
Stars, yes.
But not all neutron stars are pulsars or magnetars.
Yeah, so they're separate. They're subcategories of of each.
Yeah, and like a pulsar is usually a baby neutron star. When they first form, they're spinning very rapidly, and so they're putting out these flashes, and as they slow down over time, they turn into just regular old boring neutron stars. But something weird happens to make them magnetar.
I should mention also up there is Sextant, which also has a pulsar related. It's actually looking at the Sextant experiment on the ISS is looking at pulsar timing for navigation for deep space missions, and they're testing this on the ISS. It's an idea that you won't have GPS when you're going out into the solar system or out beyond the solar system, but you can look at the very precise timings of these pulsars, magnetars out there, and actually find your position in space, like to a very high degree.
Yeah, so they're able to use NICER, which is this instrument on ISS, and use it to look at the locations of various pulsars around, measure the way the timing of these pulsars, and measure the redshift, and calculate the position of the International Space Station to a fairly high degree of accuracy. Without using GPS or without any other system. Like, they literally measure the location of ISS, its velocity, its orbit, etc., purely based on the locations of pulsars.
Yeah, that experiment is called Sextant. But it's using NICER. It's coupled with that same mission. Yeah, no, it's kind of a proof of concept on the ISS. But
yeah, you can imagine any future spacecraft. Every future spacecraft will just have one of these on board.
Yeah,
a little pulsar measurement system, and then they'll be able to navigate themselves around the solar system. Because right now, like, even space navigation is kind of hilarious. Like the spacecraft are navigated by the time that it takes for the signals to get from the spacecraft to Earth and then back again.
Yeah.
And then they measure that and go, oh, you're a little, they know the direction to the spacecraft, and then they can tell the speed or the velocity, I guess, and then they can modify it. But the spacecraft has no idea where it is.
Sextant is the Station Explorer X-ray timing and navigation technology experiment.
Yeah, it's really cool. I totally agree. The NICER experiment is pretty great.
You don't hear a lot, but there's a lot of interesting astrophysics they're doing on the ISS, so you don't hear about it a lot. But
yeah, they have a rack on the outside of the station that you can just attach experiments onto. The nanoracks? Yeah. All right, well, let's move on. Nick, how do we get a sample back from Mars?
Well, it turns out the answer is it's complicated.
Oh. Big surprise.
So we need a minimum of 2 more missions to get a sample back from Mars. And I say minimum because some of these plans are still in flux. But what's cool is in the last month or so, NASA's actually selected a prime contractor to develop the next of these phases, which is the rocket to blast the things from the surface up into space. So here's our collection. This is an artist's rendition. The only part of this that
not a
actually
picture from
so far,
not a picture from Webb.
Not a picture from Webb. It would be a little bright for Webb. So on the left is Perseverance. In the center is a model based off of Opportunity. Spirit and Opportunity were the Mars exploration rovers, the ones that went, 11 years into their 90-day mission. That's intended to be a sample grabber. So it will go around on the surface and pick up the samples that Percy should leave behind. They're actually doing this 2 different ways, which is why they're drilling 2 cores in every location they go to. One core stays onto the rover. The other core is going to be deposited in a cache somewhere. That way, if they engineer a device that will interface with Percy and grab everything out, there's a whole set of samples that way. If they don't do that and they engineer something to pick it off from the ground, there'll be a sample that works that way. So I'm hoping they can do both because I want all the rocks, but hey, whatever. So there's a small class of rover that'll go around and pick everything up, but then you've got to blast it from the surface into space. And that's what this giant lander on the right is. The big science package of that is actually this thing that looks like a bazooka being mounted on the side. And that's the Mars Ascent Vehicle, which I'm sure is not at all a reference to the Martian, that will blow the samples from the surface up into orbit. Even once they're there, though, you still got to get Mark Watney home. So you need a spacecraft that flies by and picks up the capsule that's floating up in orbit and brings it back to the Earth. And that's what that orbiter that's rendered in the upper right is supposed to be. So the idea at the moment is that there's going to be a mission that will bring both the small retrieval rover and the lander. The retrieval rover is going to be built by the ESA. That's been part of this design for a long while now. The lander is going to be JPL, and the rocket that launches it, I believe is, wow, I should remember this detail off the top of my head. I believe it was Lockheed Martin. Wow.
I'm pretty sure it's Lockheed Martin. I think I did see that.
Yeah, I'm just feeling really dumb right now because I didn't maintain that one in my memory. Anyway, they're actually starting work on building that rocket, which is non-trivial because you need to store this rocket for probably years between final development for launch, transit to Mars, landing on the surface, being set up on the surface, and then after the samples have been retrieved, a process that could easily take a year or more, then launch into orbit around Mars.
But it's going to be making its own fuel, isn't it? It's going to make its own propellant on the surface of Mars.
So the designs are still fairly preliminary, but the designs that I've seen them put out are actually calling for a solid rocket booster to launch it from Mars' surface.
That's simple.
So we are looking at the technology for splitting Mars's atmosphere to make actually be a methane oxygen fuel source, or electrolyzing that into something a little bit larger in terms of your carbon compound. But that's not what they're talking about implementing. Solid rocket boosters are some of the most reliable. Just this one needs to be in cold storage for a long time and then set up remotely, which is also really terrifying.
Yeah.
So lots of steps and moving parts, quite literally, in this process.
Yeah. Yeah. And have you seen the tests of the sample return rocket? They've been testing them. So it gets thrown in the air and then the rocket ignites and then it takes off, which is terrifying.
Anyone who's done high power rocketry as a club sport knows that that is exactly what you don't want to have happen. When you toss something up in the air, it's really unpredictable. So this is a really hard thing to do. On the other hand, it also clears it away from your launch platform and makes sure that nothing's going to foul on the way up. So you got this trade-off.
Mm-hmm.
Of course, having seen what they managed with Perseverance and Curiosity's landing systems, if there's anyone I'm going to trust to do something this crazy, wacky, complicated, it's going to be the engineering team at JPL.
Yeah, for sure. Awesome.
I still think it's amazing that Perseverance will probably document all this. It will see it from landing to takeoff. It will be able to show us this. That's going to be really cool.
Yeah, the current timelines they're talking about, the retrieval on the surface mission would be launched somewhere between 2025 and 2030. And the actual retrieval would happen shortly after 2030. So Perseverance should still be there running because it's the same platform as Curiosity, and Curiosity is going on 11 years now.
Yeah, so. It's plutonium powered. It's good for it for a while.
It's coming. That always felt like it was going to be in the distant future, but now it actually, as you say, 20, like maybe 4 years away now. Like it's weird. Like this Dragonfly, Europa Clipper, they're actually coming fast now. Like,
and as someone who is hugely enthusiastic about sample science, I really can't wait for this. This is my version of Webb.
Getting your hands
these rocks
on chunks of Mars that are fresh, that are interesting. They're chosen because they're interesting and they're fresh, and you get to
actually one of the coolest things for me for all of this. So we sent Perseverance to Jezero because we're looking for sedimentary rocks. We're looking for fossils. We're looking for organic matter, any evidence for life. And you know what the first thing we found there was? Igneous rocks. That's my stuff.
Yeah.
Oh, it's so cool.
I think we're coming
useful for a lot of stuff. I mean, not just the let's look at the geology and chemistry of the formation of Mars, which is my wheelhouse. If we get isotopic age dates off of these, which you need an igneous rock to do really well, you can calibrate the cratering ages for Mars and really put a definitive pin in that cratering timescale so that we can get really, really, much higher degree of confidence in terms of how old all of the terrain features are. I mean, it'll just be one data point, but that's better than what we've got right now, which is nothing.
Yep. Awesome. All right. Well, I'm going to wrap up the show, give my co-hosts a chance to shamelessly self-promote what they're working on, and then we will shift over and Pamela will run the interview. So, Dave.
Frequent contributor, Universe Today, Sky and Telescope, Violence Telescopes, books here, books there, more books, like first book, second book. Astro Guys with a Z on Twitter. Usually, I tend to tweet about whatever is going on in the sky worldwide, or if anything, like this past weekend, we had a meteorite that hit north of Iceland. I don't know if you saw that. That was it was sighted. It was only the fourth time that they've seen a space rock right before it impacted. Well, it went in the ocean, so we won't recover it. So that was kind of an interesting little intriguing event that we all got the alert on that. And it was a 3 meter. It wasn't anything big, but
yeah,
that's usually what I'm
like about. Half the size of a giraffe.
Yeah,
weird measurement to get.
Is that standardized somewhere?
Yeah.
The nuclear infrasound detectors that are supposed to detect nuclear weapons detonations picked it up like off Norway, and all I could think about is like this isn't the time you want like really everybody's kind of on edge right now as far as like a Chelyabinsk type event. We don't really need that right now.
Yeah. Now is not the time for us to detect nuclear scale explosions. Kimberly.
Yes, hi. I have been publishing stuff on eos.org, as I usually do, and tweeting about it at Astrochemistry. I recently published a really fun article about how lipid biomarkers could be preserved on the surface of Europa, such that we could detect them remotely. So, like, we talk about life being in Europa's oceans, but if it's hidden there, how could we see it from afar? Turns out we probably could. So if only we knew what to look for.
Is that this story where they were like analyzing the colors of the ice and seeing if there's ways that you can actually detect the presence of these biomarkers in the ice color?
No. This is actually, they went up to the Canadian Arctic to like a really hyper saline spring in the middle of the ice to see what it actually looks like when you have bacteria or microbes frozen in really, really salty ice, and what that would look like if you could analyze it from afar with like laser spectroscopy. And then you take those and you translate that to Europa, and then you could interpret maps that come from Europa Clipper or from JUICE, and so you know where to put your future lander. It's really fun to learn all about that.
Yeah. This is the same one. This came out of Cornell, right? Yeah. Okay. Yeah, this is the same story I was looking at. Okay.
Yeah.
It's all cool.
So it's
Awesome. Like that is like one of the biggest challenges. Is like there could very well be life on all these ice worlds, and yet how would we know?
How
And
would
so
we
if
know?
there is a way, then that's how we know. Nick.
Howdy. I can now say that I'm an infrequent contributor to Universe Today, working on that. I'm also the Wandering Scientist. It's starting to get that rolling again. And I'm very excited that I can announce that I'm one of AGU's Voices for Science this year. So expect to hear a lot from me this year as I try to learn to social network and get the news out about science every which way.
Fantastic. All right,
Oh my God,
of course.
I'm so excited that next part of AGU's Voices for Science. It's such a fun program.
I'm
really looking forward to it.
2 interviews coming back to back on Friday. One about geysers on Triton, and I forget what the other one's about. But as I warned everybody, I've got just a ton of interviews coming, so buckle up. And that'll be on Friday morning. I'll put them into my queue shortly. All right. So thank you, everyone. Now, I thank you, but don't leave. So this is like a mid-show thank you to everyone, but we're going to leave. You shouldn't leave. So thank you, everyone, for watching us today. Really appreciate it. Thanks to all my co-hosts. Thanks, Pamela, for engineering everything behind the scenes. Thanks to all the administrators, moderators, and thanks to Nancy Graziano for keeping everything organized. All right, on to the interview. And thanks, everyone. We'll see you next week.
Yay.
Yay.
Okay, and they can't hear us? Okay. Nick, all right. Once again, we've got some special guests joining us on the weekly Space Hangout. Now, I'm down in this little corner here because we've got 2 guests, and I couldn't figure out a way to make everybody fit. So just like they'll start talking, don't pay attention to me, listen to them. So who are you, and what do you do?
Well, hello everyone. My name is Nashanty. I am a master's student at Leiden University, and for my master thesis, I have looked at complex organic molecules in ISS. And I am currently specializing in science communication.
Yep, and I'm Alice Booth. I'm a postdoctoral researcher. So I finished my PhD a couple of years ago in the UK, and I work here in Leiden, working with a few different things, but mostly looking at what molecules are around when planets are forming.
And you came to our attention because of a really interesting piece of new research that came out from the European Southern Observatory's press department. Anyway, they found it exciting. I found it exciting that you discovered a really intriguing molecule in a planet-forming disk. Can you tell us about this?
Yes, indeed. We discovered the dimethyl ether for the first time, and in this core, we believe that planets could be forming. And what makes this so interesting is that if we can find these large molecules in these disks, it means that they can potentially end up in planet and lead to bigger molecules, just prebiotic molecules.
So this molecule that you found, give us a sense of what it is and how it contributes here to life on Earth.
So dimethyl ether is what we call a complex organic molecule. So it's, for us, it's quite a large molecule. It's got 9 atoms. And the only way to kind of make these molecules is on the ices. So you make it on the ice, and then somehow it comes into the gas phase because it gets warmer when you have a star, and then we can observe them like we did with the telescope ALMA. But these bigger molecules, they form on the ice, and if you have something like dimethyl ether, it probably means that you have other larger molecules on the ice as well. And these larger molecules form the kind of building blocks of prebiotic molecules. So if we have the basic ingredients there, it means that more complex things can be forming.
And we've been seeing over the last few years that larger and larger and more interesting molecules, definitely ones based on that life is, needs, these building blocks of life, are being found in space. Alcohol, we've reported on many of these different molecules. Why is this one special?
Yeah, so most of these detections of these bigger molecules are happening not in planet-forming disks. They're happening in earlier stages, so either in the clouds of dust and gas that you have before a star forms, or around a very newborn star where it gets very hot. We don't actually know how much of this material makes its way into the disk where planets are forming, so we've been trying now, the kind of field has been trying to search for these bigger molecules really when planets are forming, because we don't actually know how much material is there.
So what technique did you use to actually spot this molecule?
Basically, we used the ALMA telescopes in Chile, and from that we, of course, received data. And from this data, we can, from a master, I made a spectrum. And from the spectrum, we can analyze it. And by using models, we can identify these molecules by looking at special features in the spectrum.
And I guess, based on finding this molecule in this planet-forming disk, and you mentioned some of the steps that had to go on, sort of a multi-stage affair to actually reach a molecule this big and this complex. What do you think this means for the kinds of molecules that were present on Earth early on in its history, when it was still kind of a magma hellscape?
Yeah, so I think it's still an open question as to how much the actual volatiles are on the Earth when it forms, but we know that comets are very rich in organic material, like 67P even has glycine on it. And so the kind of observations that we're doing of disks, we can relate these back to the compositions of comets. And if we know solar system comets are full of organic material, and we can show that in disks, the same places planets form, comets form in the same regions, if we know we have those molecules in the disk, then it kind of all connects back.
And so not necessarily present on the planet, but present in the solar system and delivered, by comets or asteroids or some combination of them. Where do you think this ends? I mean, each couple of years we're seeing more and more interesting complex building blocks of life. How far up the chain of life do you think we're going to be able to get?
I think it'll be difficult, because as we go to more complex molecules, the abundances or the number of molecules we have get lower. So we kind of get limited by the sensitivity of our telescopes. Obviously, we keep building bigger telescopes, but there's a limit to that as well. So I think maybe in a few special objects we can find some really big molecules, but I think there'll be a limit, right? If you have the building blocks, though, we know we can make things from experiments in laboratories.
Right. So we're limited by the telescopes, but not necessarily limited by the molecules. Like I'm sort of envisioning, I wonder, based on these multi-phase affairs where various molecules are coming together and forming more complex things, is there a conceivable limit on, obviously I don't think we're going to end up with RNA. That would be lovely, or DNA, but is there kind of a limit to how big theoretically these molecules can be coming together I mean, I guess what I feel like is like you went out looking for a specific set of molecules, chemical signatures. Is there some other, are the theoreticians cooking up what they think are the possible molecules that you think you might find in these clouds and in these accretion disks?
Well, for future studies, we're obviously going to look for molecules that have similar formation routes as the one that we detected, which is the methyl ether. But we're also going to look for example, for nitrogen bearing molecules as well. So by finding these molecules, it gives us an idea of what we should be looking for next.
Yeah, and also a lot of it is driven by actual laboratory astrochemistry. So in the labs here in Leiden, they do experiments with ices, and they take simple ices and they evolve look and see if what you can build out of these ices. So they start with just say water and CO2 or CO, carbon monoxide, and they see how you can make more complex things. So once you have a certain number of molecules, we know a pathway to make something more complicated. So we don't necessarily need to find the most complicated molecule if we have the building blocks.
Right. So how do you think this changes the story of, I guess, abiogenesis, just this idea of how life first started out on Earth? Does it make you feel like the universe was preparing the life a lot better than on Earth? Does that make sense?
Yeah, I mean, we're mostly observational astrochemists, right? So this is getting beyond our kind of bubble of expertise.
It's just us. No one's going to watch this. Don't worry about it.
But I mean, the very early years is not a very hospitable place. But there are other places in the solar system, like you have some of the moons on other planets have a lot of ices and a lot of potentially kind of organic, prebiotic, like soupy material. I don't know. But I think we're very lucky we're on this planet, I think.
Yeah. I guess it just feels like when I think about, say, the conversation that were being had 20 years ago, or when they first did their first experiments, like to try and figure out how life started, and you just had a bunch of organic chemicals and you zapped them with lightning and tried to saw amino acids starting to form and so on. There was this expectation that all of the building blocks here on Earth were very simple, like carbon and oxygen and nitrogen and so on, and then things got constructed in more and more complex forms. But now, with this discovery of all of these atoms in more complex forms, it feels like what was being delivered to the Earth was far higher up the complexity chain than Earth having to cook this all up on its own.
Yeah, absolutely. I think it's still kind of, people are researching how much, say you have a comet impact the Earth, what happens to that material as it passes through the atmosphere? How much of it makes its way on Earth? There's still a lot we don't understand, I would say. Yeah.
And do you think that the work that you're doing would give us some ideas on how to search for this here at home in the solar system?
Yes, definitely, because as I said, now that we know that these molecules are present, we also want to expand our search, because we can deduce from this that they're not only present in this disk, but they can also be present in other disks as well. So it gives us an idea of where to look and what conditions we have to look for to find these molecules.
And I guess if you could get a sample in the lab from somewhere in the solar system to help you understand this better, what would you like delivered?
I mean, like some comet would be nice, probably.
Yeah.
But I mean, you can do remote observations of comets as well. So using
we're going to deliver a comet right to the lab that you can work on it.
Yeah, I mean people would like that very much, I think. Yeah.
All right. Well, it's absolutely fascinating research, and it just kind of goes to show that the story of life on Earth is a lot more complex and a lot more interesting than I think anyone had ever sort of thought. So congratulations on making this discovery, and I look forward to even more complicated molecules next.
Yeah, thanks for being interested in talking to us, and it's really great for Nashanty as a master's student to work so hard to put together a paper. It's a real achievement, I would say.
Congratulations. Thank you. Take care.